Deep inside a quiet suburban neighborhood, a heavy green box sits almost hidden in the tall grass near the road. On hot summer afternoons, thousands of home air conditioners turn on at the exact same time. The air outside grows thick with unbearable heat, and the thin wires humming overhead carry a massive burden. Deep inside that dark green box, copper coils struggle under the sudden violent pull of electric current from every house on the street. For over 100 years, the electric power grid relied on traditional transformers to move energy into homes. These old machines were simple passive devices built from solid iron cores and tightly wrapped copper wire. They were static pieces of metal that could only drop dangerous high voltage down to a fixed lower level. They had no eyes to see changing local needs and no internal tools to fix sudden spikes in the flow of electricity. In the old days, electrical power moved in only one single direction. Massive central power plants burned coal or harnessed falling river water at giant dams far away. They pushed high-voltage electricity out along heavy steel towers, sending energy down a straight path toward growing cities and quiet rural towns. Engineers built those old transformers for a world where energy always flowed down from the big plant directly to the kitchen light bulb. That simple world vanished when bright solar panels began to cover suburban rooftops. On bright summer afternoons, thousands of neighborhood homes stop pulling power from the grid and start sending their own extra energy backward into the local distribution wires. The old wire network was never designed to handle flow in two directions at once. Electricity pushes back against electricity, causing unpredictable pressure to build up inside the neighborhood lines. When too much power floods backward from rooftop solar arrays, local voltage climbs to dangerously high levels. Lights inside nearby homes flicker brightly, and sensitive electronic circuit boards inside television sets and kitchen appliances begin to cook under the high heat. Without proper voltage control, whole streets face burned home appliances and sudden electrical fires. The old static system simply cannot keep up with the fast shifts of modern power creation. To stop the destruction of local power lines, modern electric utilities are replacing old pole hardware with a smart transformer. This new hardware creates a massive shift in how electrical energy travels through our towns. Instead of relying on fixed iron parts, it uses active management to measure local power levels every single second. It acts as a digital gatekeeper designed to keep line voltage smooth, clean, and completely safe. At the heart of this modern hardware design is a fast set of solid-state power electronics. Instead of using heavy mechanical switches that wear out and spark over time, this system relies on advanced semiconductor chips. These solid-state switches open and close millions of times each day without mechanical failure. They act like ultra-fast digital valves, trimming excess voltage before it can overflow into the thin wires leading into your home. Inside the transformer casing, smart sensors monitor the exact voltage of incoming and outgoing electrical waves. When the system detects a tiny wave of extra voltage coming from a neighbor's solar roof, it responds in less than a millisecond. Fast-switching power semiconductors chop up the extra current, lowering the output voltage back down to safe operating levels before any home appliance on the street can feel the sudden surge. The immediate difference out on the neighborhood street is instant and complete. As dark rain clouds pass over a sunny suburb, rooftop solar energy production drops to zero within a few seconds. The old grid would suffer a sudden drop in voltage, dimming lights and straining refrigerator motors. But the smart transformer senses the sudden drop instantly and boosts line output, keeping the lights inside every home running steady. The challenge grows even larger as late afternoon arrives, and families drive home in heavy electric vehicles. Dozens of high-power EV chargers plug into home outlets along the exact same small street at the same moment. Each charger pulls a deep wave of electric current out of the power line, creating a severe drag on local voltage. Without help, the electrical pressure in the line sags like a heavy rope. Here, active management shows its true power against heavy human demand. The software-controlled brain inside the smart transformer recalculates circuit needs hundreds of times every second. It adjusts internal magnetic coupling and shifts power routing electronically. instantly raising output voltage to cover the deep pull from charging car batteries. The neighborhood grid stays calm and level, absorbing massive spikes in power demand without a single light flickering. Down at the local corner bakery, heavy commercial baking ovens turn on while large refrigerators blast cold air to keep ingredients fresh. In years past, a sudden neighborhood voltage drop would trip main circuit breakers, shutting off ovens and ruining full batches of fresh bread. Today, continuous voltage management keeps commercial bakery machines running smoothly without interruption. The local business keeps working, completely unaware of the power shifts outside. This solid-state technology shift changes the relationship between small local power circuits and giant regional utility grids. Old high-voltage transmission lines were built to carry massive steady power across hundreds of miles, but today, power generation is broken into thousands of tiny pieces scattered across home rooftops, wind farms, and local battery banks. Managing local voltage protects the main transmission grid from collapsing under the stress of scattered energy sources. Severe winter weather brings a different kind of extreme physical hardship to the suburban grid. Thick freezing ice coats overhead utility wires while thousands of electric heating units switch on inside dark bedrooms. The extreme cold lowers line capacity while doubling energy demand across whole counties. In severe storms, old mechanical transformers often fail or burn out, leaving thousands of cold families trapped in total darkness for days. Solid-state electronics do not freeze or wear out under extreme winter strain. Inside the smart transformer, specialized converter circuits change incoming alternating current into direct current, then rebuild a clean alternating power wave at the exact voltage needed by homes. This two-step power conversion isolates the local neighborhood from wild surges on high-voltage transmission lines, creating a reliable bubble of steady power during the worst winter storms. Inside the central utility command center, wall displays show real-time digital data streaming from thousands of smart transformers across the city. Grid operators no longer have to guess where power lines are failing or send utility trucks into dangerous winter storms to replace blown fuses. Clean digital signals tell engineers exactly how much power is flowing, allowing automated software systems to balance regional grid voltage with extreme precision. Across large industrial manufacturing plants worldwide, automated assembly lines build these advanced devices to replace millions of aging utility pole transformers. High-purity silicon carbide and gallium nitride wafers are carefully etched to form high-voltage semiconductors capable of handling thousands of volts. As factory production scales up, the cost of smart power hardware continues to drop, making complete grid modernization possible for cities and rural towns everywhere. In a quiet suburban bedroom late at night, a young child sleeps peacefully while a delicate medical monitor runs on the wall nearby. Out on the dark street, cold wind blows heavy rain through aging power lines, while rooftop solar panels sit completely dark. The hidden work of active voltage management goes on without making a sound, protecting human lives from dangerous power drops and destructive electrical spikes. As electric shipping fleets and massive artificial intelligence data centers expand across the nation, human energy demands will grow far beyond anything seen in past generations. Millions of high-power devices will place unprecedented stress on every wire, transformer, and power station. Static hardware built for the old industrial age cannot handle this massive scale, making software-controlled voltage management essential for the stability of modern human society. Engineers continue to improve silicon carbide chip architecture, creating smaller and far more efficient transformer systems. These advanced solid-state materials handle much higher temperatures and extreme power loads without breaking down under heat stress. By packing high-performance power electronics into compact weatherproof enclosures, utility companies can upgrade neighborhood power poles without replacing existing wooden poles or digging up expensive city street pavement. The total transformation of our electrical infrastructure represents one of the largest engineering projects in human history. We are turning a passive, rigid network of simple copper wires into a dynamic, intelligent system capable of sensing and adapting in real time. Every smart transformer installed on a suburban street pole is a vital building block in this massive, quiet shift toward a fully automated world. Outside, the green transformer box sits quietly in the dark grass as night settles over the neighborhood. Cars finish charging quietly in driveways, and warm lights shine through living room windows along the block. Deep inside the sealed steel casing, fast, solid-state electronics switch millions of times per second, managing voltage silently to keep the invisible power of modern civilization moving forward without a single pause.